Hello, everybody. Today, Dr. Yu Morishita will present us StriX small SAR satellite constellation. Dr. Morishita, could you please introduce yourself and please welcome to your presentation.
Yeah, thank you for introduction. So let me start my presentation. Hello everyone. Good evening, good morning, good afternoon. I am Yu Morishita from Synspective, Japan. Also, are you seeing my slides? Okay.
Yeah.
Okay. Yeah. Okay. So yeah, today I'd like to talk about StriX small SAR satellite constellation. So first, let me introduce myself. So I started my career at Geospatial Information Authority of Japan, GSI. This is one of the governmental institute in Japan. And there I used EROS and EROS-2 satellite, L-band SAR satellite, and I worked on InSAR, MT-InSAR algorithm development and operation for nationwide deformation monitoring, mainly for Japan, and earthquake and volcano researches. And during this period, I got opportunities to stay abroad, and I stayed at TU Delft in the Netherlands and University of Leeds in UK. And yeah, I used various kinds of satellites like this, and I worked on temporal declaration, MT-SAR algorithm development, and especially in the University of Leeds, I developed ISPRS software, which is an InSAR time series analysis software, and I published it as an open source software on GitHub repository. And yeah, this software is now used by many users in the world. And also I published a ISPRS paper in a journal, and this paper has been cited more than 300 times. So this is one of my research highlights. And in 2022, 3 years ago, I decided to leave GSI and academic government sector, and I moved to the industry sector, and I joined Synspective. Yeah, this is today's main topic, and yeah, I joined Synspective as an SAR application engineer, and here I use our own satellite, StriX, and I also use other satellite data, and work on the MT-InSAR algorithm development and operation. And at the same time, I have a position in AIST, a kind of, yeah, second job, and I partially continue some academic research, mainly using EROS-2. Yeah, so today's main topic is Synspective and StriX. So let me introduce Synspective. Yeah, Synspective was founded in 2018. It's 7 years ago. And the headquarters is located in Tokyo, Japan. And we have some branches in Singapore and USA. The number of employees is currently more than 200. And we have a global team from 23 countries. So there are many non-Japanese employees. Yes. And yeah, our mission is this one, to create a new infrastructure that enables the next generation to understand our Earth and achieve a resilient future. So as you know, the global risks such as disaster, security, environment has been increasing. And to help protect ourselves against these risks, it is essential to quantitatively visualize and understand these risks. And this requires data that is homogeneous, stable, and extensive on a global scale. And we believe we can make this possible through our small SAR satellite constellation. And why we chose the SAR satellite constellation. And there are several reasons, and one is the reliability. So SAR satellite, a satellite-based SAR observation provides reliable, standardized, and long-term data across the globe. And another one is availability. So SAR is unaffected by cloud cover or darkness, unlike optical sensors, and it can provide global accessibility. And the third one is technology. So advances in miniaturization and cost reduction democratize access to space-based observation. Frequent low-cost launches enable scalable constellations for higher temporal resolution, and high-performance computation and StriX accelerate data utilization from raw signals to actionable insights. And these are the Synspective's business model. So we have three main pillars. Three pillars in our business model. One is SAR satellite constellation. Another one is SAR data. We sell the SAR data. And the third one is providing solution services. So let me explain more about this. So we manufacture our own satellite, small satellite, and the name of satellite is StriX. And one of the characteristics of this StriX satellite is its size. It's very small, only 100 kilogram class. And the traditional large SAR satellites like Sentinel-1 and Eros-2 have much heavier weight. It's more than 1,000 kilograms. So it's more than 10 times heavier than StriX. And the big satellites need a lot of cost to manufacture and also launch because it's very heavy. And in other words, StriX satellites can be manufactured and launched with very low cost. And it enables us to manufacture many satellites, and we can construct the constellation with many satellites, and it enables us to acquire the high frequency data. So this is a very key value of the SAR constellation. And we sell these the SAR data acquired from this StriX satellite constellation. So these are our important business model. Make the SAR data and sell the SAR, manufactures the satellite and sells the SAR data. And in addition to these ones, we also develop and provide the solution services. So this is our unique point. And as you know, SAR satellite data itself is quite difficult to use, quite difficult to extract the insight from SAR data because SAR data has very complex and low visibility and wide area and large volumes of data. So to process the SAR data and to extract the insight from SAR data, we need expertized knowledge and technique. And we also need some automation to process huge amount of SAR data. And we have these knowledges, SAR data processing, remote sensing, and data science. And so we ourselves develop the solution services to fully exploit our own SAR data and using other data as well. And we also have an advantage to develop the solution because we have our own SAR data. So this is the very unique point of Synspective. We are the data provider and the solution provider both. So this is a launch and operation history of StriX satellites. So we have launched 7 StriX satellites, and the first one was launched in 2020. And currently we have 4 satellites in operation. Yes. And this is manufacturing and launch plan of StriX satellites. And now we are in 2025, and we have 4 satellites in orbit. And next year we will launch 7 satellites, and we will have 11 satellites in orbit. And currently, with 4 satellites, we can observe a specific area on Earth, everywhere on Earth, with a daily frequency. And next year, with more than 10 satellites, we will be able to observe a specific area every few hours. So this is quite big improvement. And our short-term goal is to construct the 30 satellite constellation around 2028, around in 3 years. And if we have 30 satellite constellation, we can observe a specific area on Earth every hour. So this is our short-term goal around 2028. And yeah, we also improve the performance of the satellite from second generation to third generation. So we have launched some second generation satellite, and its capability, imaging capability was 15 images per day. But in the third generation satellite, we have 40 images per day. So it's quite big improvement. And yeah, to launch many satellites, of course, we need to manufacture many satellites at the same time. And we have already increased the production capacity like this, and by opening new factories in Yamato and Nasu City in Japan. And now we have the annual production capacity of 8 satellites. And next year, we will further increase the capacity to 12 satellites. So that's why we will be able to achieve 30 satellite constellation in 3 years. And we will launch more satellites in next year and more. Yeah, so this is a future plan. And yeah, next I will talk about the StriX observation modes. So we have 3 different observation modes: strip map, sliding spotlight, and sliding spotlight. So each mode has different coverage, spatial coverage, and spatial resolution. The strip map mode has the widest coverage. Swath width is 20 kilometers, and the azimuth length is 50 to 7 kilometers for one scene, and it can be extended to 500 kilometers. And the spatial resolution is about 3 meters. And the sliding spotlight has narrower coverage, about 10 by 10 kilometer, but the resolution is much higher, 1 by 1 or 0.5 meter. And the steering spotlight mode has the narrowest coverage, 10 by 3 kilometer, but it has the highest resolution, like 0.25 meter. So depending on the target or use case, we can choose the most appropriate one. So for example, if we want to cover wide area, but we don't need the very high resolution, we can choose strip map mode. Or if we need to focus on very small infrastructure, we can choose this steering spotlight mode. Yes. And another characteristics of StriX constellation is its orbit type. So we have 2 different orbit, sun synchronous orbit and mid inclination orbit. And yeah, most of the big satellites are in this SSO orbit. And in this orbit type, the satellites reach to North and South Pole, and it can achieve the global coverage. So this satellite can observe anywhere on Earth. And yeah, our StriX Alpha, Beta 1, 2, 3 have this orbit, SSO orbit. And yeah, another unique point of StriX is this repeat orbit. So these satellites have 1-day repeat orbit, so very short repeat orbit to conduct the frequent observation. And yeah, in addition to this SSO orbit, we also have different orbit, which is MIO, mid inclination orbit. And in this orbit, the satellite doesn't reach North and South Pole, but the benefit of this orbit is the frequency in the mid-latitude region. So we can observe the mid-latitude region very frequently compared to the SSO satellites, so including Japan area. And StriX 4 and 5 have this MIO orbit, and the repeat orbit is 5 to 7 days. Yeah, so here is an example of the StriX image acquired by Sun Synchronous Orbit satellite, and yeah, daily revisit. So this is Singapore area, one of the ports in Singapore, and we can clearly see the movement, daily movement of the ships like this. And yeah, we also developed the data platform. And in this data platform, users can search our data archive, and users can order and download the data. And also users can request the new acquisition and download the data. And we have also prepared the API so that users can integrate our system into their platform. And currently, this data platform is not publicly available, but registered users can access this, and you can register your user account by contacting us. So there is a contact form on our website. So if you are interested in accessing this data platform or interested in purchasing our data, please contact us. And from here, I would like to show some use cases using StriX data. And first one is the disaster response. This is very important use case for StriX satellites. And we have provided the data mainly to the government. And we have responded various natural disasters like earthquakes, typhoon, and landslides. And in the disaster response, one of the most important point is the delivery timeline or latency. And this is one of the flat case this year. And this is a timeline. And in this case, the acquisition was done around 3 p.m. And the tasking deadline, in this case, was set 1.5 hours before the acquisition. And that tasking was conducted here, and the acquisition was done here. And after that, the data, which means the SLC data, was delivered to the customer 0.7 hours after the acquisition. So this is quite fast. And also, the first report change detection or first insight was provided 1.2 hours after the acquisition. So this is also very fast. And so this means from the tasking deadline to the first report delivery, it took less than 3 hours. So this very short latency is quite important and quite useful for disaster response and first action of the disaster response. And after that, we also created the more detailed second report, flat analysis, and it was also the 3.2 hours after the acquisition. So this is very short latency is one of our strong points. From here, I will show some examples. So this is Noto Peninsula earthquake example. In 2024, there was a huge earthquake on January 1st, 2024. And we observed this area by our StriX satellites, and we identified the damaged area using the change detection algorithm. Like this, caused by the wildfire. And most damages are collapsed. And this is a Los Angeles wildfire case. And in this case, we used colorized subaperture image analysis. And in this analysis, we use a single data captured by steering spotlight mode, which have relatively long synthetic aperture lengths. And in this analysis, we assign a different color, RGB, to different synthetic aperture time like this, and we create one color composite image from one single data. And this is a CSI image, and this colorized part shows the man-made structures, and these white ones shows the damaged buildings. And from this colorized image, we can distinguish the damaged building from the non-damaged buildings. Next case is the inundation caused by typhoon. So we have this post and pre and post event, post disaster images, and by comparing these images, we can clearly identify the inundated area, and we created such polygons using an algorithm, and we clearly identified the flat area from our StriX data. And the last one is the volcano use case in Shinmoedake in Japan. So June 2022, this year, Shinmoedake volcano erupted for the first time in 7 years. And we have conducted the continuous observation with high resolution mode and very frequently, almost daily. And we have identified the topography change caused by the eruption. So this is the existing big crater, and inside of this crater, a new crater or crack was created like this. And we have identified the location and the shape of the crater clearly with very high resolution mode like this, 0.25 meter resolution. Yes, so these are the use cases of the disaster response. And also we have some solution services for normal time. And for example, object detection and classification solution. This is mainly for D&I sector. And we have land displacement monitoring using InSAR technique for ground foundation and infrastructure analysis. And these are the disaster response. And also we have environmental analysis, including forest inventory management and offshore wind and wave. So among these solutions, this land displacement monitoring uses InSAR technique. And honestly speaking, we haven't used StriX data in this solution. And currently we use other SAR satellite data like Sentinel-1, TerraSAR-X, Cosmos SkyMed, and EROS-2 and 4, because the StriX satellites have not achieved the stable orbit control. But in the near future, of course, we aim to achieve the stable orbit control, and we want to use our StriX data in this solution. So from here, I would like to talk about the InSAR related things and the new solution using our StriX InSAR data. So this is my field of expertise. So first, let me start with the brief theory of InSAR. So we use two data acquired at two different timings. And if there is a surface displacement between two acquisitions like this, the distance between the satellite and the ground surface changes like this. And this change of the distance can be measured by the phase difference, by computing the phase difference from these two data. And we can make this rainbow colored interferogram representing the surface deformation. So this is InSAR. And the most important factor for InSAR is the baseline. So baseline means distance between two satellites at two acquisitions. And the important component is this perpendicular component, perpendicular baseline. And this is a geometric declaration equation. And this means if the perpendicular baseline is larger than the critical baseline, and critical baseline can be computed by this equation, we cannot get any coherent signal from like this. And if the perpendicular baseline is significantly smaller than the critical baseline, we can get perfect coherence. So this means keeping the perpendicular baseline much smaller than the critical baseline is essential for InSAR. And that's why most of the big satellites set such orbit tube, narrow orbit tube, and keep their orbit inside within this orbit tube. However, as I said, StriX have not achieved such stable orbit control, but we aim to achieve stable orbit control in the near future. And however, we have some opportunistic InSAR demonstrations. Yeah, we had some InSAR capable data from StriX satellites, and we created some InSAR programs using StriX data. So from here, I would like to show some examples of the StriX InSAR programs with different conditions, like one-day interval or MIO InSAR program and cross-platform InSAR program. Yeah, so first example is this one-day interval long strip map interprogram. So in this case, the StriX satellite observed the Kyushu area in Japan from north to south. And yeah, this is strip map, so the azimuth length is quite long, 235 kilometer, and this can be extended to maximum 500 kilometer. And yeah, range source width is 20 kilometer. And yeah, as we can see, we can see clear fringes here in this differential phase. And yeah, this area is, yeah, there are some urban area like here, but most of the areas are covered with vegetation like this. And in general, expansor data is difficult to get coherent signal on the vegetated surface. However, in this case, we successfully obtained the clear fringes and some sufficient coherence on the vegetated area, some of the vegetated area. So this is probably because of the very short temporal interval, one day. So this means if the temporal interval is very short, like one day, we can still use the expander interferograms on vegetated area. Yeah, next one is the MIO interprogram. So we used StriX for satellite in MIO orbit. And yeah, we can see the clear fringes and yeah, high coherence. And we can also see some decorrelated signal along the roads like this. And yeah, the important point is this one, azimuth direction and range direction. So in this case, the azimuth direction is almost toward east, northeast, and the range direction is like this. So this, the important point is that this interprogram has north-south direction sensitivity, unlike SSO satellite. So by combining with SSO satellite interprogram and the MIO satellite interprograms, we can retrieve complete three-dimensional deformation. Yeah, so next example is cross-platform InSAR using StriX 2 and 3. So this is Shinmoedake volcano case. Yeah, this is intensity color composite image, and this is a differential phase. We can see clear fringes, and but this is during the eruption period. But I don't think these phase changes were caused by the deformation, because this area is generally suffering from the intense atmospheric noise, and from this spatial pattern, I think this is caused by the atmospheric noise mostly. But the most important signal here is the coherence. Yeah, we can see the low coherence area here, and the newly created crater was located here, and at this timing, the wind was from southwest to northeast, and the volcanic ash accumulated around here. So this decorrelated area represents the volcanic ash accumulated area. So this coherence image can be useful to identify the volcanic ash areas. Yes, so I have shown some opportunistic StriX InSAR data. But so what can be the applications of these StriX InSAR data? So for the big SAR satellites like Sentinel-1 and Eros-2, so they have different characteristics from StriX constellation. So they have always very small perpendicular baseline and global coverage, constant observations, and long and large data stack. So this these pixar satellites are quite suitable to multitemporal InSAR and wide and slow displacement monitoring. But on the other hand, StriX Constellation have the local coverage and tasking based of the patient, so we don't have the global coverage, constant global coverage. And in the near future, currently we haven't achieved the stable orbit control, but in the near future we will be able to achieve the stable orbit control. And once we achieve it, these StriX Constellation data can be used for multitemporal InSAR, and it can enable us to conduct the high resolution and frequent displacement monitoring like infrastructure and mining. So this is a promising use case for the StriX Constellation satellite data. But currently we have no stable orbit control. However, even limited condition, we can still get some insights from StriX interferogram, and it is height measurement. And we developed a new technique to extract the height change, and we call it InSAR TDEM. So let me explain about this technique, InSAR TDEM. Yes. First, let me start with the theory of height measurement using InSAR. So this is a single pass InSAR case. Single pass InSAR is not for StriX. Tandem X and Terasa X can conduct the single pass InSAR, but it's very limited. Only these satellites can do it. Like bistatic or tandem operation. And this is an interferometric phase, and interferometric phase contains various components like atmospheric noise, orbit noise, displacement, topographic phase, and decorrelation noise. And in this case, single pass InSAR phase, because there is no time difference, this interferometric phase doesn't contain the atmospheric noise or displacement. And the decorrelation should be also very small and ignorable. And from this single pass interface, we can accurately extract this topographic phase component. And this topographic phase can be written by this equation. And these are the known parameters, and we can extract this one, height signal. And we can construct the DEM with very high accuracy from this single pass data. However, as I said, the single pass InSAR data is very limited, and we cannot access it. But we have plenty of repeat pass D-InSAR data, like Sentinel-1, EROS-2, and StriX as well. But the problem is that this repeat pass D-InSAR phase contains these other components than the topographic phase. So generally, it's difficult to extract this topographic phase, but in some limited condition, we can extract this topographic phase. For example, if the temporal interval is very short, like 1 day interferograms of StriX, the displacement should be very small, and the decorrelation should be also very small. And also, if we focus on the height difference from DEM, not the DEM itself, this signal of interest should be localized generally. And this signal can be distinguished from these signals, atmospheric noise and orbit noise, because they are spatially smooth, and we can separate these components by applying the low-pass filter. So this is the main concept of the InSAR DDEM analysis. And there are some important factors to conduct InSAR DDEM, and it is perpendicular baseline and wavelengths. So next, I will explain about the sensitivity to height change. So this equation shows the relationship between the height change and topographic phase. And here is the perpendicular baseline and wavelength. So these are the important factors. And this figure shows the relationship between perpendicular baseline and the height sensitivity to the height difference. And yeah, as a reference, I set the upper limit pi radian, in which we don't need the unwrapped phase. And for the lower limit, I set the pi over 5 radian, considering the phase noise. And yeah, for example, this orange band represents the sensitivity area for L band, L2, and for satellite. Yeah, for example, the L2 satellites have the orbit tube with 500-meter diameter. 500-meter diameter. So it means we can get the 500-meter perpendicular baseline at maximum generally. And it means that this means the 500-meter baseline corresponds to the 10-meter DH sensitivity. So this means we cannot measure smaller height change using this data. So the sensitivity is not enough for meter order height change. And the same is true for Sentinel-1. Sentinel-1 has much severe, strict orbit control, and the perpendicular baseline is generally 100 meter or less, and the sensitivity is around 10 meter. So we cannot measure the meter order height change from this data. But for X-band data, like here, for example, 300-meter baseline corresponds to the around 2-meter sensitivity. So we can extract the small height change from X-band data. So this means X-band data is quite suitable to this application, InSAR DDEM analysis. Yeah, so here is the InSAR DDEM workflow. So we use the two SLC data acquired at two different timings. This is completely same as the normal D-InSAR analysis. And also we use the reference DM. And yeah, important point is this one. We need to select the short temporal baseline pair and the appropriate perpendicular baseline pair to have the sufficient sensitivity to height. And we create the InSAR image interprogram like this, and we remove the long wavelength component by applying the low pass filter, high pass filter, and we get this interprogram. And after filtering and phase unwrapping, we convert this phase to DH using this equation. And we get the height difference from DM like this. And adding back the reference DM to height difference, we get this refined DM or DSM. And yeah, this refined DM reflects the topography around the SAR observation dates. So this is the latest new topography. And the resolution depends on the SAR data resolution, not the reference DM. So if we use Copernicus 30M DSM as a reference and we use 1 meter resolution SAR data, we can get the 1 meter resolution DSM. So it's the resolution can be improved from reference DM by applying this technique. Yes, this is the InSAR DRAM timeline. Yes, and to compare this is conventional InSAR and pixel offset timeline. So in order, this is a elevation change event, and generally for InSAR and pixel offset, we create a data pair spanning this event. But this deformation includes complete surface condition change. We cannot get any coherent signal, and we cannot measure any deformation from InSAR and pixel offset. But in this InSAR DDEM analysis, we use two post-event data like this and create the interprogram, and we can measure the height difference from DM, including this elevation change event. So this means for InSAR DDEM, we don't need any archive data. So this is the good point for InSAR DDEM technique. And also the latency is very important, and StriX can create the interprogram with 1 day interval. So we can measure DH only after 1 or 2 days after the event at the earliest. So I will show an example of this DDEM analysis in Japan Sakurajima area. So this is a reference DEM and the optical image, and we can see the flat area here, and the DEM is flat, and I created this entire program and converted to the TH height difference component. And yeah, this is an optical sensor, newer optical image, and yeah, we can clearly see something was constructed here, and this TH component represents this structure. So I successfully measured the maximum 15-meter height change with meter-order accuracy. And in order to evaluate the accuracy of this DDEM measurement, I compared with newer DEM created around 2022. So the acquisition timing was a bit different, but mostly the same. And yeah, this is DEM difference between these two DEM height difference, and this is a DEM analysis result from this reference DEM. And yeah, the residual is quite small. And yeah, so this means we have achieved the meter-order accuracy using this technique. Yeah, so yeah, this InSAR DDEM technique can be applied to these phenomena like slope failure, dam collapse, illegal embankment, mining activities, sediment deposition, and volcanic activities. So we can measure the height change caused by these phenomena using InSAR DDEM analysis. Yeah, so this is the last slide in my presentation. Yeah, so we Synspective is building a small cell satellite constellation, and our StriX satellites can deliver high resolution and frequent revisit. And yeah, we can provide fast response and actionable insights, and we also develop the advanced analytics. Yes. Yeah, that's all from me. Yeah, thank you for your attention. Yeah, thank you very much.
Okay, okay. Thank you very much for your nice presentation. And we have some question for you. It is in question and answer part, if you can see, or I can read for you.
Yeah.
The first question is, how does the expand design of the StriX satellite influence the types of application Synspective prioritized compared with L-band or C-band SAR constellations? This is the first question.
Okay. How does expand design? Yeah, L-band and C-band constellations. Yes. Yeah, so this is the general characteristics of expand, but yeah, so expand satellite can generally achieve high resolution. So L-band satellite cannot achieve 1 meter resolution. And yeah, it's 3 meter is maximum, I think. And yeah, so expand is generally suitable for infrastructure or yeah, small structures, man-made structures. And yeah, why we chose expand is that I think so we are a commercial company and we need to make money and yeah, we need to contribute to the society and the of course, the focus is mainly on the urban area or human society or yeah, populated area. And yeah, for these applications, the expand was the most suitable. So so our main application is the like infrastructure or mining or human activity related one rather than the natural science or yeah, earthquake volcano. Yeah, of course, we include earthquake volcano use cases, but the main focus is the yeah, urbanized area or infrastructure rather than yeah,
Yeah.
other things. Yep.
Okay, thanks for the answer. And the second question is StriX data will increasing the support in SAR applications. In this case, what challenges do you foresee when integrating X-band InSAR time series with data from other missions like Sentinel-1 or ALOS-2?
Mm, yes, thank you for your question. Hmm, challenges integrating. So I am not sure, but I don't think we integrate the expand time series analysis with other satellite data. So we have different characteristics, and Yapixa satellite C-band Sentinel-1 EROS-2 time series analysis is quite suitable for the large area continental scale or nationwide scale monitoring. But our satellite can focus on the very localized area, and we can get very high resolution and high frequency monitoring. And yeah, so it is a kind of integration maybe, but yeah, so we have different characteristics, and yeah, we have compromising characteristics. So I think, yeah, we can get the synergy effect using both satellite for wide area monitoring with mid resolution and very focused area monitoring using our expand SAR data. Yeah, so this is the answer.
Okay, thank you very much for your answer. And the third question is, what would be the preferable frequency for uplink and downlink for a CubeSat GCS?
I, I'm sorry, I cannot understand this question. GCS, what does it mean? And I don't know much about the CubeSat, so I think it's not related to the StriX constellation. So I think I cannot answer this question.
Okay, okay, thank you. And one more question we have. Which real-world use cases like urban subsidence, infrastructure monitoring, disaster response, etc., are currently showing the strongest demand for StriX data, considering that you are producing it professionally?
Mm, yes. Yes, strongest demand is. Yeah, I would say it's the disaster response. And yeah, as I said, unfortunately, we cannot create the inter programs constantly. So we cannot conduct the InSAR analysis and we cannot respond to the urban subsidence analysis or infrastructure monitoring. But for the disaster response, our StriX data is already very useful because of this very short latency, and the intensity data is quite useful to detect the damaged area, or yeah, like this wildfire or inundation or water flood damage or volcanoes. Yeah, so currently, this disaster response is the most demanding application. But in the future, of course, if once we can conduct the InSAR analysis stably using StriX data, this will be the very important and very high demand use case. Land displacement monitoring will be the high demand use case, I think.
Okay, thank you very much. We have two more questions. Do you anticipate StriX expanding beyond X-band or integrating with other sensor types, for example, optical or GNSS-R, in future missions?
Yes, yeah, this is a good question. And I have shown the future plan like this until 2028. And we haven't decided the further future plan. Of course, the directors are thinking about it. And yeah, there are many possibilities to expand our business, yeah, integrating other sensors, of course, like yeah, optical sensors, hyperspectral or IR or RF or something. And yeah, we are considering which is the best sensor to combine with our expand satellite. And yeah, also, yeah, yeah, other than the other sensor types, other possibility is other band, like L band or other band is also another possibility. But yeah, we haven't decided it yet. And I don't know actually. But there are many possibilities in the future, mid-term or long-term.
Okay, thanks again. And the last question is StriX also coming with ascending, descending constellation?
Ascending, descending constellation. I am not sure what it means, but this is a normal satellite, and we both have ascending and descending orbit. So it's already available. We have, both ascending and descending data for each satellite.
Yeah, you're right. I guess these are the all questions if I did not miss any. Uh, Thanks again for your nice presentation. It's really very useful and full of knowledge. Thank you very much. And I think we can close the session if there is no question more. Okay. Thanks a lot, Dr. Morishita.
Yeah. Thank you very much for your attention.
Okay.
Thank you.
Okay.
See
Bye.
you.
Uh, Thank you so much. So is it okay for me to stop the recording then?
Yeah, I think yes, there is no more question. The other chat part has only people introducing themselves, but there are some questions, I guess, there as well. Sorry, I missed them, but okay. I think a few more questions there, but we missed it already. One more question. Okay, there's a question about getting some sample data for educational institutions. What is the mechanism to get data? I think free data or open data. They are.
Yeah, sorry, I dropped. So there is on our website, we have the data gallery and we publish some open data as a sample data. And I am not the salesperson, but I heard that there is a discount for educational institute, universities. I think there is a discount. So please contact us and sales member will respond it.
Okay, thank you very much. I think all the questions are covered. Thanks again, and
Thank you.
thank you for coming back and answering us. Thank you.
Yeah.
Okay, thank you very much.
Thank you
Bye.
very much.
Okay.